Ready? Next section is odd basis set transforms. And by odd, I don't mean strange, although they may be strange as well. I mean formally mathematically odd functions such that an odd function f of minus x equals negative f of x, as opposed to an even function. Again, I'm just dusting off cobwebs at this stage, where f of minus x equals f of x. And all functions can be decomposed into a combination of even and odd components. Okay, odd basis set transforms. We're going to go through three. I'm going to, again, spell them all out for you first, and then work them through explicitly. So the first one is sine to an odd double delta. Indicated by delta delta minus with a characteristic frequency f0. And we will go into each of these in more detail. So I'm just very briefly outlining what the three basis set functions are, and then we'll go through them. The second one is also sine. And that transforms as reciprocal. How do you spell reciprocal? Yes, SIGN. So it is sine, but it's a different kind of sine. Basically, it changes sign across zero. I've become to rely so heavily on spell check that I'm terrible at spelling now. Reciprocal? Okay, thank you. That won't be at all embarrassing. And then the third is the derivative, which Fourier transforms as the diagonal. That's what. That one's the funkiest. Okay, so let's go through each of these in turn, starting with the first sign. So for the sine function, does that. It has a characteristic crossing at t0 if it's defined this way, right? If it's defined as 2 pi t over t0, then the first zero crossing is at t0. And this is an amplitude of a and a characteristic time of t0. Then its Fourier transform partner looks like that. This will be 0 when sine is equal to pi, as well as 2 pi. Yeah, it seems like it should be t0 over 2. Should also have a crossing there. Okay. And that gives us an odd double delta, just as the name implied. Just as we had the even double delta for the cosine, we had an odd double delta for a sine. What's the amplitude? The amplitude here is, negative I a over 2 and I a over 2, depending on which of those two double deltas you're looking at. Which of the two deltas you're looking at. Why I? Darn it, it's got that square root of -1. Shows up everywhere in Fourier transforms. Can't get rid of it. unless you just do everything with even basis sets. Yeah. An I is a 90-degree phase shift. So if our reference frame is cosine being real valued, then everything that is odd is complex, purely complex in the Fourier domain, because it's 90-degree phase shifted. So all of the odd Fourier transform pairs will result in complex amplitudes across that Fourier transform relationship. Okay, on to the next sign. This one has no characteristic time constant. That is the sine function. I'm just going to rewrite that so it's clear. So its Fourier transform is the reciprocal. It's 1 over pi f scaled by a and multiplied by negative I. And it diverges at 0. Yeah?
Is the f in the numerator or denominator?
Denominator. Denominator. Numerator. Moving on. All right, the last one is the derivative. Yeah, given a Fourier transform relationship between f and phi, then if I take the derivative with respect to f, what is its Fourier transform? It's a sneeze. The Fourier transform of this is multiple. It's phi of f multiplied by I 2 pi f. So this will have if f equals 1, the amplitude of that is I 2 pi f, or I 2 pi. I'm going to point out another thing that might not be obvious. I just want to emphasize it in this one because we'll actually use it. If we do d df of phi of f, that Fourier transforms in the exact same way, but of course with a sign change in the I term. Why is there a sign change? Because we're going to go from time to frequency, we have a negative I. We multiply by e to the negative I 2 pi ft. And for the inverse Fourier transform, we multiply by e to the I 2 pi ft. So there inherently should be a sign change in the... Now, we don't see that in the real part, in the even functions, because they're all real valued. But in the complex functions, we do see that sign, that complex term, change sign, depending on if you're going time to frequency or frequency to time. So in this case, that would be actually f of t times negative I 2 pi t. All right, now it's probably not clear yet how we're going to use all of these basis set transformed or basis set functions and combine them and manipulate them into solving complex problems yet, right? We had one example that hinted toward it, and my goal today is to get through a healthy chunk of the toolkit, and we'll exercise that on Tuesday. So that's the plan right now. So if it seems like you're sort of getting too many things to keep your head around, that's okay. You can forget about them all weekend, and then I'll expect you to have them at the tip of your fingers, ready to go first thing on Tuesday. So you'll have a chance to brush up on the weekend, get them all memorized. It actually is useful to memorize these. I mean, I hate memorization as a general rule, because I don't think that there's anything you should be forced to memorize that you can't easily look up on your phone. Because you always have it with you, always, except for OPs. But other than that, always. Yeah.
So, can we go back?
Sure.
So how does this one relate to amplitude? You said amplitude is 1.
So if I look at this part of it, right, then when f equals 1, the amplitude of this line is I2 pi. It's just basically to acknowledge that the slope is I2 pi.
Little f equals 1?
I'm sorry?
You said when f equals 1, you mean frequency.
Yes, when little f equals 1, yes.